Hello everyone, welcome to PCT Lecture 9. Today we will discuss about Laplace Transform and how to apply it to power circuit theory. We will discuss about the transient response of a circuit when the fault happens, and we will use the Laplace Transform to analyze it. It is kind of related to your circuit analysis before, so it's a updated review for you. And after that, we will discuss a very interesting phenomena, restriking voltage. So first we discuss about Laplace transformation, which is a transformation between the time domain and the S domain. So in the time domain, we have a few basic functions like this. It has the same characteristic as before t equals 0. Everything starts at 0, so there is no signal. But after t equals 0, suddenly the signal appears. Either it jumps from 0 to 1, or jump from 0 to a linear function, or jump from 0 to a cosine function like this, or jump from 0 to sine function. Here we have a decaying function. It also jumps from 0 to the decaying function. And if we multiply it with a linear function, we see that it rises first linearly but quickly decaying with the boundary of the green one here. For the cosine and sine function, we also have the same characteristic, so it will also appear at the cosine or sine, but the amplitude of the cosine and sine will be decaying over time, so the oscillation will never fall out of the green boundaries like this. The key point is that if we look at the S domain, they're all very simple, and we will use these functions to analyze our circuitry later. So let's have a look at the transient response example here of a RLC circuitry. Here we have the circuit's constant like this, and the voltage is just a sinusoidal signal of a 200 volt grid single phase. The frequency is 50 Hz. So at t equals 0, we close the switch. We need to determine the instantaneous current after the switch is closed. So first, we need to convert the circuit to S domain. Notice that now it is quite similar to J omega, but we just replace the term J omega with S. So R resistor will become 2 ohm normal. The inductance, the impedance of the inductance is SL. It will be 0.2 S. And the impedance of the capacitor will be 1 over SC, which is 9 over 5S like this. So we need to convert the voltage as well, following the Laplace transformation table. Here we have 220 volt times cosine omega t and ut here, indicating the operation of the switch at t equals 0. So Vs here will be 220 times omega over S square plus omega square. And we will draw the circuitry using the new values in the S domain like this. So the circuit analysis in S domain is exactly the same with our normal analysis. First, we need to find the total impedance. So Zs here is the total impedance of the three components in series, which is 2 plus 0.2s plus 9 over 5s. And then when simplify them, we find that it is s squared plus 10s plus 9 over 5s. So the current is Vs over zs like this, and just replace this and this into the formula. We have the result here. Notice that here I will just keep the omega here so that you see the form clearly, and then I will replace omega with 2 pi f here, which is 314.2 radian per second, and we can have the form that's we have only the variable s. So this is our current in the s domain. We don't see any t here, just s. So next, we'll try to expand our current expression by using partial fraction expansion method. Sometimes it is called decomposition method. So the essential part is that we know what our equation look like, and then we try to decompose it into a simple expression like this. And then we can decompose it further using a sum of a constant over s plus a constant like this. So here we have 4 of them because our degree at the bottom is 4. So essentially we should have 4 terms ABCD. So here we can apply cover up method, which is that we look at the original expression and try to cover the individual part. So for example, if we look at A, the part that coming with it is s plus j 314.2. So we try to cover it, and when we try to cover it, we look for the value that make it become 0. So s should be equal minus j 314.2 here. Then we replace that s to the remaining equations and calculate it. So the result will look like this. It is minus 2.544 plus j 0.08966. The same thing for b, but here we can see that because for b we are looking at the conjugate s, so the result is that b is actually the conjugate of a. For c and d is the same, but we don't have any imaginary part, so we have only real number. So after finding ABCD, I write it down like this, and you can use the Laplace transformation table already, but what I want to do is to get rid of this complex constant. So I merge them together, and we see that when we merge them together, the term s square plus 314.2 square or omega square appear here. On the top we have 56.34 minus 5.088 s. We can decompose it like this, and here this part look like our basic Laplace function already, but this part doesn't look like it because on the bottom we have s square plus omega square on the bottom. It doesn't look similar on the top, so I make it look similar by dividing this number with omega, and then I get 0.1793. So I have omega appear here, and then everything will become simple if I replace the 314.2 with omega. So here we have the basic Laplace transformation. Everything will appear here, and we need to look at our Laplace transformation table and convert it into the corresponding time domain function. So at the end, the omega over s square plus omega square will become sine omega t. The terms s over s square plus omega square will become cosine omega t. The terms 1 over s plus 1 will become exponential of minus 1 times t, and the terms 1 over s plus 9 will become exponential of the minus 9 times t. The rest will remain the same. Notice that the step function ut is not displayed here because it is the transient after t equals 0. So next we will discuss the restriking voltage phenomena, which happens right after the fault and the circuit breaker open to protect our circuitry. So let's imagine that we have a voltage fall happening here. So when the voltage fall happens, we have a short circuit and all the current will flow through this inductor. This capacitor is short circuit. So the flow current will be sinusoidal like this. And the system voltage that appear here at the sending end look like sinusoidal. And because it's inductive, so the voltage leads the current, or the current lags the voltage. Now we need to open the circuit breaker to protect our device. And because this is large current and we have an inductor, so it is very essential that we have to wait until the current reaches 0 and then we open the circuit breaker. So let's assume that the circuit breaker open here when the current is 0 and the voltage is peak as Vm, like this. We see that the circuit breaker voltage before it open, it remains 0 because it's short circuit. But then when it open, normally we expect that it will jump to the real voltage here, but no, it doesn't. Instead, it will jump to very high and then oscillate and then go back to 0 or go back to the normal voltage system. We call this transient behavior. And after that, the voltage is cover the voltage of the system, and we call this one recovery voltage, back to normal. Our assumption is that there is no resistance in the line, it's lossless. The magnitude of the impedance is assumed to be the same. All the effects like saturation and corona will be neglected as well. Charging current through the transmission line will be neglected. The flow interruption occurs at exactly the point of 0 current here, or the voltage is maximum when opening the circuit breaker. So let's have a closer look at our circuitry. The flow occurs here, and we can use current cancellation method, or it's a kind of superposition theorem to figure out the voltage across the capacitor here. The result is quite simple. The result of the method say that the voltage across the circuit breaker will equal the current during fault multiplying with the Thevenin impedance of the network looking from this side. So VC equal IF times Z Thevenin, like this. So first, because the fault is very short, so it looks like we are applying a step voltage of the magnitude of Vm to this circuitry. The current during fault IF will becomes V over S over Z, like this. So it Vm over S over SL. The Thevenin of the network looking from this side is actually we have to short circuit this one, and then look from this side, it will be the inductor in parallel with the capacitor. So the impedance is the two impedance in parallel, like this. So when we try to apply the uh, IF and ZTH into this formula, we have this, and then we decompose it into this form. And here we can convert it back to the time domain, which is here. V maximum multiplying with 1 minus cosine 1 over square root of LC times T. This is a omega 0, which is the natural frequency of our circuitry, or is the natural frequency of our LC circuitry. It's not 50 Hz. In fact, it is very high frequency. So we try to plot the voltage waveform across the circuit breaker. It looks like this. So before we open the circuit breaker, the voltage across the circuit breaker is 0 because of the short circuit. Right after that, the voltage will rise and oscillate with the frequency omega equal 1 over square root of LC. So we can find out that the first peak occur when the omega t equal pi, or t equal pi times square root of LC. And the peak happen here is twice the maximum voltage that we discussed. And because we assume that there is no resistance and the line is lossless, the oscillation will continue forever. But in reality, it will be damped back to normal after a short while. In reality, if we have a long transmission line and then the fault happen in the middle here, and we open a circuit breaker in the middle, then essentially we have two circuits, the right hand side and the left hand side, and they have different oscillation frequency. So we call this phenomena double frequency transient. This is the end of our lecture. For your homework, please practice tutorial 9